Welcome back, students. We will continue our discussion on the magnetic field due to current carrying conductors and the strength of the magnetic field. We are going to take what is called as a solenoid to figure out the magnetic field within the solenoid or around it, due to the current flowing through a solenoid. Okay, first of all, what is a solenoid? Solenoid is a spring-like structure. Like this is, you see, this can be considered as a solenoid if you think about it. It's a spring-like structure. So at one end, the current will start, it will enter the solenoid and then continue to flow through the solenoid, and then it will exit at the other end. Okay, so that is. Okay, let me just try to. Yeah, you got it. Messed up. Anyway, so I think you can understand like what I mean by that, right? So this is more like this is the solenoid. The structure of a solenoid is like a spring. Current will enter at one end and then leave at the other end. So it will go into the solenoid like this. Now the question is, what is a magnetic field? Maybe like inside the solenoid and also outside the solenoid because of the current that is flowing through the solenoid. Okay? So the way to do that can be different for different approaches. For example, if I'm going to take the Biot-Savart law approach to find B at a particular point around or inside the solenoid, then what should I do? I have to take a current element IDL for each, and I have to take the current, each and every current element within the solenoid IDL, and then find B due to those current elements at a particular point. Okay? Field due to current element 1, field due to current element 2, field due to current element 3, and so on. And I need to add all those things vectorially to find the resulting magnetic field. Okay? That is one way of doing it. But it's going to be, you can see that it's going to be mathematically very complex. And if you remember, I've told you that that wherever you have a mathematically complex situation, you can probably explore the possibility of using the Ampere's circuital law, so that the mathematical difficulty gets reduced. So that is exactly what we're going to do here. Well, I want you to understand the discussion that we've just had. To find the magnetic field due to a solenoid at any particular point, the basic approach, the fundamental approach, is to take the current elements, the innumerable current elements in the solenoid, and then find out the B, the magnetic field due to individual current elements, and finally vectorially add them. That is the most fundamental way of doing things. But if you do it that way, then the approach is going to be mathematically complex. It's not that you can do it, you can do it, but then the mathematics involved will be a little difficult to do. But if you take the Ampere's circuital law approach, it could become easier. Let us see what we can do here. Okay? So let me talk about the solenoid here. The solenoid is this kind of a structure, right? It's like this. So this is the solenoid. It's a spring-like structure. Okay? So if current flows through it, then the field will be set up, right? So the field will be set up as the current flows through this. I can find the direction of the current using the right hand rule. For example, if suppose the current enters here, comes like this, okay, and it makes this circle and then it goes like this, and if it leaves here, then clearly you can see that it goes like this, and I can expect B to be in this direction. Okay, so you see, so B inside the solenoid can be in this direction. Okay, but you see, it's not just the single element, right? I mean, I can expect if you look at the picture in your textbook, it will tell you like this. Okay, if you look at this picture, you have the magnetic field around every loop, right? And effectively, that magnetic field, see, there will be a magnetic field around this, and this, and this, and this, and every point will have a magnetic field, and they kind of like you will have this kind of a structure effectively. You will have, you know, straight lines in the center, and maybe something like this here outside. Okay. So it's like that. Okay, the field will be something like this. It will be like this. Okay, the current would be entering here, and then, you know, it will be leaving here. So it will enter here, enter this point, and then leave that point. You know, it's like this. It will be like this. And if I consider this solenoid to be pretty long, you know, it's very long compared to, I mean, the length is much bigger than the radius of the solenoid, let's say. So long, and then it is so thin. Okay. In that case, what I can expect is something like this. Okay. Small. Okay. Solenoid is like this, right? Let's say. This. So you see, outside, if you go further here, then I can clearly expect the field set up by this current element can be cancelled by the current element in the bottom. Why? Because there it will be entering, and at the top it will be entering, the current will be entering at the top, and it is like a circle. Let's see, like a circle now. The current will be entering here, and then it will be leaving here, right? So enter, leave. So if you take a point here, far away from there, this ideal will put a field there, and this ideal will put an opposite field there. So if you are far away from here, so then what will happen is there won't be much difference between this field, and they will cancel each other out. Now that is the reason why we are even talking about a solenoid like this. We are considering a solenoid which is pretty long. The length of the solenoid is large compared to the width of the solenoid. So that just outside, if you see, the field set up by one can be cancelled by the other. It will happen to every current element. For a current element that is going this way, it will put a field there. But then you have an equivalent current element on the other side that's going down. This could be going up, and that could be coming down. So when this current element puts a field, that will put the field in a direction opposite to the direction of this ideal. Okay? It's like this. You take a small circle, it's a current is flowing like this. Suppose I take a point here. So this will put a field here, right? So this current will put this ideal. You take this ideal, that will put a field like that. Okay, it will go in. But then this ideal, it's going this way, so that will put a field. It's coming out here. So this and this could kind of cancel. If this distance is negligible compared to this distance, and it will kind of cancel here. Likewise, if I take this one, if I take this current element, that will put a field here, and then that will be cancelled by this current element. And you can see that the resultant field outside the solenoid could be 0. So, I mean, if you can do it for one circle, then you can expect the same for all the other circles. So, the point here is that you have a long solenoid whose length is much greater compared to the width of the solenoid. Okay? So, then that results in field B being 0 here, and then the field will also be 0 here. But inside they will aid each other. You notice, like if you take this point, let's say if you take this one, you see current is flowing this way, current is flowing this way. So you see it's like this, right? Inside it will be coming out. Again here, if you take this, current is flowing this way, so inside it will again be coming out. So they will aid each other. And the same thing will happen to all these things. So all these current elements will provide their own magnetic field inside the solenoid, and they will aid each other, they will add up. But outside they will cancel each other out. So you will have a B here. So the B would be like this. So then how do I find the value of B there? Okay. So that's the question. Let's say that I have a certain number of these windings, okay, number of turns per unit length. Let's say I have so many, okay, turn per unit length. I mean, total number of turns is it's huge, but I'm just going to consider only the number of turns per unit length. So I'll say that is number where n is equal to number of turns per unit length. So if I need to find how many turns are there in any particular length L, then that would be n times n. Okay, so that is it. Let me take that point. Second is, I am going to consider an open surface, an Amperian surface. Okay. What did we say when it comes to Ampere circuitry law? We said that the closed loop integration of B dot dl of an open surface is equal to mu naught times the current piercing through that surface. Okay? So what I'm going to do is I'm going to imagine a surface like this. A surface like this. Okay? So let's say this is length L. Maybe this is length B or something. Okay? I'm going to imagine this surface. It's like a paper. So it's like, take this. Okay. Assume that this is going into the paper. Okay, so there are many turns. It's like you have a spiral binding notebook, right? So it's like that. Like you're seeing this as a spiral bound notebook. Okay. So what you're going to get here is this. Okay. So that spiral. It's like a spiral binding notebook. So goes in. So the current, so if I is the amount of current that is flowing through it, then you can see that I goes through the surface once, and then again twice, thrice, 4 times, 5 times. It's like that. Okay. So let's see. So then what I should do now is that if I take this surface, this paper-like thing, and if I do a B dot dl along this direction, and then do a B dot dl along this direction, and B dot dl along this direction, B dot dl along this direction, then that B dot dl, integral B dot dl, the closed loop integral B dot dl of this surface, of this open surface, must be equal to mu naught times the amount of current which is piercing that surface, right? You see, it's not just I that is piercing, because you have so many turns, I. you need to find out the amount of current that is piercing through the surface. So in one turn you have I current. So if you take this length L, how many are piercing? It's going to be N into N. So that's the total number of turns, total number of piercings, penetration, and then into L. Each penetration will have I there. So this is the expression I get. Okay, now I need to find B, right? So B is here. I have some B here, right? B is here. So it's constant B. You can from the shape of the lines you can see that B is constant here. Outside B is 0, right? So B will be, you will have B here. Okay, I'll just use this. So B is like you have B here, B here, B here. So there is some B here, and B is outside. B outside is 0. Okay. Now how do I do the integration? Okay. Well, I'll start from here. I'll say this is A, this is B, and this is C, and this is D. So this can be written like this. This can be written like integral A to B. Okay. Then B dot dl plus integral B to C, B dot dl plus integral C to D, B dot dl plus integral D to A, B dot dl. This must be equal to mu naught n L to I. That's what it is. Okay, let's see. So here inside you can expect B to be constant, right? Because the contribution will be equal on both sides because it's a very long solenoid. So, and it's like a straight line there. So B is constant. I can take B out. So B is in this direction, and DL will also be in the same direction, right? DL is also in the same direction here. So B and DL will have an angle of 0 between them. So cos 0 will be 1. So it's simply B DL into 1. So that gives me A to B DL. And then 1. Cos theta will be 1. That is done. Okay, so then what happens here? It's the second one. Here, well, this can be split into two parts, right? I'll say this is B to C dash and C dash to C. B to C dash and C dash, because you see within the solenoid we have B, but outside the solenoid B is 0. Okay, so this can be split into two. Then I can say that this is going to be equal to B to C dash, B dot dl plus C dash to C, B dot dl, and then plus say C to D, B dot dl plus B dot dl. That is, again, when it comes here, D to A dash and A. Okay. And D to A dash plus A dash to A, B dot dl. Okay. So this is equal to mu naught NL to I. Same thing. Let's do this. Let's see what will happen here. B to C dashed. B to C dashed. B here, you see, you will have B in this direction. And what about DL? DL is in this direction. You see, it's perpendicular to B. So cos theta will be 0. So this integration at this one will become 0, because even though you have B and also DL, but the cos theta is cos 90 and that value will be 0, so this will become 0. So I can ignore this. Then what happens here outside? Again, dl is in this direction. Here, c dash to c. Is there a b there? No b. Because outside we said it is 0. Right? Because this is so thin that outside we can ignore the b. So, b is anyway 0 and dl is also perpendicular to is in this direction. So, this here also this will be 0. This will be 0. B will be 0 anyway and the whole thing will become 0 there. Again, now what about CD? Again, CD, even though you have DL in this direction, what's happening there? B is 0 outside, right? B is 0. So this will also be gone. Okay, and what about this? B dot DL, A dash, from D to A dash, D to A dash. Again, that will be 0. Why? Because B is 0 here, from D to A dash, right? So this integral will still be equal to 0. And A dash to A, well, you will have B here anyway, B in this. B is not 0 because you are inside that path. But then, the DL is perpendicular to B. So the cos value, cos theta value will become 0 because the angle is 90 degrees. So cos 90 is 0, so this also will become 0. See, here you have B, it will still be 0. Here also you have B, it will still be 0 because B and DL are perpendicular to each other. But at all the other places, all the other 3 places, B itself is 0, so they will contribute nothing to the B dot DL integral. So all these terms are gone, so you are left only with B, then A to this B, and DL, which is equal to mu naught, and then N L into I. Okay, but A to B, we keep adding DL, 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 DL. We keep adding, then this will give you the length L. Right? This integral will give you length L because integral dx is x, right? So integral dl will be L. That's exactly this length. Okay? So B L is equal to mu naught N L I. L and L can be cancelled. Then you have B is equal to mu naught N to I. So this is a magnetic field inside the solenoid. Outside it is 0. Why is it 0? Because you are considering a solenoid which is pretty long and the thickness is very small. The width of the solenoid is small compared to the length of the solenoid. So you can expect the B to be 0 outside and B to be constant inside. So this is what you get here. Okay. So this I'll say as the magnetic field inside the solenoid. Magnetic field inside the solenoid. So let me the title is magnetic field due to a solenoid. So the takeaway is this: you have a solenoid. A solenoid is a spring-like structure where current enters at one end and then leaves at the other. And if you have a very long solenoid whose width is negligible compared to the length, okay, or diameter, I should say, the diameter of the solenoid is negligible compared to the length of the solenoid, then you can expect B to be nearly 0 outside the solenoid and to be constant inside the solenoid, as you can see in the picture. Okay? And once you have this kind of a structure, inside the field structure, then using Ampere's circuitry law, you can find out the value of B inside. Okay? And for that you are imagining a square surface, or a rectangular surface, I should say, not even square, rectangular surface, and you consider the solenoid to be piercing through the surface. So you do a closed loop integral BDL of this open surface, and we're going to equate it to the mu naught times the amount of current piercing through the surface. Even though I is a current which is flowing through the solenoid, we cannot take I straight away, because you have to take the number of times it is piercing through the surface, right? So that is going to be n into L, where small n is the number of turns per unit length multiplied by whatever length you take. Anyway, that length will drop out of the equation, because you will have one L here also on the right hand side, and then on one and on the left hand side. So then L's will cancel, and ultimately resulting in B being equal to mu naught n times I. Okay. So that is a magnetic field inside. Outside it is 0. So that is field only inside. Hope this is clear to you. So the next item on our agenda is the toroid. We are going to find the magnetic field inside a toroid. And what is a toroid? A toroid is nothing but a closed solenoid. It's like this. Okay? You make a solenoid, and then you just kind of close it like in a circular fashion. I mean, it's not coming out neatly. Anyway, so it is so the toroid is of this shape. Okay? Let me just. So it's like solenoid, and you're closing it like this. Okay? See, it's like a solenoid, like a spring only. Okay, so it's like a spring only. Okay, but then you're closing it like this. Okay, so this is a toroidal structure. So again, let's imagine that it is a current flowing through. I is a current flowing through it. So clearly, suppose if I is a current flowing through it, then I can expect B to be in this direction, right? B is in this direction. Okay. And as usual, you also imagine that this is small compared to the radius of the toroid. Okay. It's now at the circumference of the toroid. Compared to circumference of the toroid, and the thickness of it is small. Let's suppose that. And let us see what is going to happen. Okay. Well, I can find B inside. There could be B inside, because it could be B inside, and then there could be B outside, and there could be B outside. Okay. Here, this part inside, the outside of the inside of the toroid. Okay. So if you make a like a circle, then inside that circle, okay, which is actually outside the toroid, but inside the circle. Okay. That part, this is B, and this is another B, and there is another B, which is actually inside the toroidal structure. That this is B. Well, this is B1, this is B2, this is B3, and the other one is outside the. Let us see what will happen. Okay, one thing is, let me talk about B1. So for B1, at some point at B1, so what I will do is I'll imagine, suppose I want to find B1 at this B1 at this point. What I'm going to do is I'm going to imagine an Amperian surface like this. Okay, that's an Amperian surface I've got here. So what should I do now? I need to do a B1 dot dl of it, right, around that surface, and then I equate it to the amount of current piercing through that surface, right? Okay, I call this as B1 in surface 1. Okay, that's what I'm going to say. So in surface 1, let us see what will happen. surface 1. So B1 dot dl, I'm going to have a closed loop integral. So that integral is going to be around this, right? So this around this. Okay. And this must be equal to mu naught times the current piercing through the surface. Well, okay. Is there any current piercing through this surface? No, it's inside the solenoid, right? So this is inside the toroid. It's like this. We're talking about this surface. So is there any current piercing through that surface? No current is piercing through this surface, right? This particular surface here. So this mu naught times I is actually 0. So this will become 0. So the closed loop integral B1 dot dl for this open surface, we call this as this surface. Okay. Is actually equal to 0. And notice here, B1, just purely by symmetry, suppose if there was a B1 here, and that would be the same here also. But you see, the same number of elements will contribute to this point and also to this point, which is they're actually from each and every current element, and they're almost at the same distance. If you notice, for example, this may be closer to this current element, but further to this current element. But then you have this. If you take this point, it is closer to this current element and further to this current element. So that way they're symmetrical. All the points here are very symmetrical. So if at all they had a B, then that would be a constant, correct? So B1 would be a constant, and then dl you can have, right? So dl, so that would be a closed integral. So that is actually equal to 0. But you see, dl would give me, if suppose this is a radius, and all these dl will give me 2 pi r. So b into 2 pi r, I'll call it as r1, okay? 2 pi r1. So that must be equal to 0. You see, 2 is not 0, pi is not 0, r1 is also not 0. So only b has to be 0 to meet this condition. So b, since these are not zeros, so b must be equal to 0. So there cannot be a field outside the toroid, it's inside. In the inside part of the toroid. Okay, so I should say, okay, this is again, it's outside the toroid orbit, but it is inside of the outside. Okay, so and then this is outside of the outside at B3. Let me try to do this for this surface. Okay, I'll take that surface B3. Okay, I'll use a different color now. Let's say, let me take this circle. Let's say I want to find B at this point. So this is going to be my surface. And red is the surface. And then you can imagine that they're going and then coming out, and going and coming out. You see, current is piercing and then it is coming out this way. It's going that way as it pierces it, and then it's coming out this way, right? So you see, the amount of current that is piercing will be equal, the amount of current that is going outside would be equal to the amount of current that is coming inside. So resulting in net current 0. I want you to understand this. If I take this surface, suppose if I take this surface, okay, let's say like I have, see in the case of the solenoid, you had only this partially, it was going like that. But now in this case what you're doing is you're taking it fully. It's taking it fully. It's like this. Okay, taking it fully. In fact, we're doing it at both places, but I'm just talking about one. You see here, this part will pierce through it and this part will come out of it. So the amount of current going into that would be positive and the coming out of it could be negative. So this I will cancel with this I. So the net amount of current is through that surface. The net current which is piercing through that surface is going to be 0. Same thing here, we are considering this surface, right? So for S3, say for S3, I do this B dot and B3 dot DL is equal to mu naught to the amount of current. It will cancel. You will have both positive current and also negative current, right? So you will have both positive and also negative. So if you add those two, then they cancel each other out. So that's going to be 0 again. Okay, that is gone. Okay. Now, what I'm going to get here. So again, because of symmetry, this point, if it has a B value, this point will also have the same B value because of symmetry. You see, this element, this closer to this element, and then slightly further, and then maybe like slightly further here, or much further, and then much further. So all these things will contribute something, if at all they contribute there, and that would not be any different from B at this point, because this will do the job of this, and this will do the job of this, and this will do the job of this, and this will do the job of this, right? Anyway, so this point and this point are symmetrical. Okay, so if at all it has some B3, this will also have the same B3. So I can take B3 out. Take B3 out, and then integral dl. See, in that case, we are going to keep all these dl's, and finally that will result in the circumference of this circle. So, and if that is R3, this is R3, then I am going to get what? To mu naught into 0. It is going to be equal to B3 into 2 pi R3 is equal to 0. Again, 2 is not 0, pi is not 0, R3 is not 0. So B3 must be 0. So here again we'll say B1 is 0. Then here B3 must be equal to 0. So there is no B here or here. Once you have a toroid, there is no B outside the toroid, and also there is no B inside the toroid, or inside of the outside of the toroid. So both B1 and B3 will be 0. Now that leaves us with B2, this particular area, part of the toroid, which is inside the toroid. What would that be? Again, for this also, I am going to consider a circle inside. So notice here, this circle that's an area, right? So you see, only these are piercing. Okay, so only these are piercing, and these are not piercing because they are outside the circle, they are not piercing. So I'll take only the amount of current that is piercing. Okay, so let's see. Again, if I have the B must be same, right? For this also, I take this, that is this S1, and this must be S2, and that was S3. Okay, this was S3. This was S3, right? But now I am focusing only on S2. Okay, only on S2. So this is piercing, this is piercing, yes, piercing. But like there is no return path for that. They are just piercing, they are going in. Okay, like coming out in all these cases. just coming out. Okay, now for S2, what are you going to have? The same integral B2 dot dl must be equal to mu naught times mu naught times this. Well, let's say that I have 1, 2, 3, 4, capital N number of piercings, number of turns, capital N number of turns in the toroid. 1, 2, 3, 4, 5, 6, 7, N number of piercings, turns, right? So that's going to be N times then I. Okay? So that's the amount of piercings, current penetrating through that. Even though I is a current which is flowing in every turn, there are N turns, so N penetrations are there on the surface, so Ni. You see, this is not going to cancel like this. Why would it not cancel like this? The reason why it would not cancel like this, okay, I can also say why would it not cancel here is because you are going to have no, you are not going to have this return path because your surface is limited here. Okay, inside. That is why it won't cancel like this. But here in the S3 surface, this was going in, this was coming out. So you are cancelling exactly. But that is not going to happen here because you are getting only one type of penetration, either coming out or going in. That's it. So mu naught to Ni. Again, by symmetry, B2 can be taken out. B2 can be taken out, and that is going to be equal to dl. It's close to dl. The mu naught N into I. Okay, so what are you going to get here? So that dl would give you, let's say this is R. Okay, maybe this is R2. R2. Okay. So this is going to be B2 into 2 pi R2 is equal to mu naught N by I. So now what is B2? It's inside, right? B2 is equal to mu naught N by 2 pi R2 to I. So what is this basically? N is the total number of turns and 2 by R2 is a circumference. So what does it give you? It gives you small n. What is small n? Number of turns per unit length. So there are capital N number of turns in this length. So capital N divided by that length will give you the number of turns per unit length. So this also gives you mu naught into N to I, where N is the number of turns per unit length. Okay, so that's what you get here. So again, we generalize it. B inside B2 is actually B2, which is inside the toroid. That can be written as B is equal to mu naught Ni. You see, in both cases, whether you took a solenoid or a toroid, then B is always inside these things, and that is equal to mu naught times N times I, where N is the number of turns per unit length. It's not the total number of turns, it's the number of turns per unit length. So if you wind the wires tightly, then you will have more turns per unit length, right? So in that case, for the same amount of current, if you have wound the wire tightly so that you have more number of turns per unit length, then B will be greater for the same amount of current. Okay? So that is what you have to understand from this. That the same thing happens to both solenoid and also toroid. A solenoid is a spring-like structure. A toroid is like a solenoid, but it's closed at both ends. It's like a take a spring and then close it at both ends, make a circle, and that becomes a toroid. Okay, so that's about it. So I hope this is clear to you. And we are balanced without any materials, any magnetic materials inside. So you get mu naught Ni, but if you have magnetic materials, then this will become something else. It will become mu into Ni, but that is for a different class. At least, see, I want you to understand this. So B is equal to mu naught times N times I, where N is the number of turns per unit length. It's not the number of turns. It is the linear turn density, should call it that way. So number of turns per unit length. So the tighter you wind the coil, and the greater you can have B for the same amount of current. Hope that's clear to you. Okay, now let's do an example problem. Example 4.9. A solenoid of length 0.5 meter and a radius of 1 centimeter is made up of 500 turns. It carries a current of 5 amperes. Then what is the magnitude of the magnetic field inside the solenoid? Okay, you see, the length is given to be 0.5 meter, that's 50 centimeters, and the radius is given to be just 1 centimeter. So for half a meter, then you have only 1 centimeter as a radius. So like you can say that length is much greater than a radius. So you can use a long solenoid formula we've just derived. Right? B is equal to mu naught Ni. That formula can be used because the length here is much greater than the radius r. So that is example 4.9. So let's see what is given here. What else is given there? So solenoid of length of 0.5 meters, and then radius is 1 centimeter. That is 10 power minus 2 meters. And then there's the total number of turns. N is actually 500. So that's 500 turns. Okay? This solenoid has a 500 turns. Not per unit length, it's total number of turns. And the amount of current that is flowing through the solenoid is 5 amperes. So you have this kind of a structure. Okay. So that length is 50 centimeters, and this radius is just 1 centimeter, and the current which is flowing through that is 5 amperes, and the total number of turns, capital N, is 500. Okay, so what do you know? You know that the B outside can be treated to be 0, well, it's a long solenoid, so B outside can be treated to be 0. So they want only B inside. So for the B inside, the formula is simply mu naught N into I, and you have mu naught, and then you also have I, which is 5 amperes. But note here, this N is not this N. This is total number of turns. This unit had to take it as number of turns per unit length. So what is the number of turns per unit length? So N can be given as total number of turns per length. Okay, so that is number of turns per unit length. So what is the total number of turns here? 500. What's the length? Which is 0.5 meters. So this will give you 1000 turns per meter. So that small n is 1000, because you can clearly see that for half a meter you have 500. So for 1 meter you would have had 1000 turns, right? So that is what you need. So mu naught N is equal to 1000 turns per meter. Okay. So now B is simply mu naught, which is 4 pi to 10 power minus 7 into N, is simply 1000 turns per meter, and then the current is simply 5 amperes. Okay, so what are you going to get here? So this will be 4 into 5, 20, 20 into 1000, 20,000, so 10 power minus, so is equal to 2 into 10 power 4, 20,000, right? 4 into 5, 20,000 into pi into 10 power minus 7. So this would be gone, minus 3 is what you'll get. So 2 into 3.14. 2 to 3.14 would be equal to 6.28 into 10 power minus 3 Tesla. So the magnetic field inside the solenoid, so constant magnetic field inside solenoid is equal to 6.28 into 10 power minus 3 Tesla. It's a very straightforward problem. The only thing here is that you have to find n. They have given you capital N and then the length. Okay. So using that you can find this n, which is the number of turns per unit length. The unit length here is 1 meter. And the length of the solenoid is only half a meter. So for half a meter you have 500 turns. So for 1 meter you would have 1000 turns. And once you get the value of n, you just use the other things, which is simply 4 pi into 10 power minus 7 for mu naught, and I is 5 amperes. Okay. R is given only to decide whether to use this formula or not. R is given only to do this. Okay. Or you are not going to use R in any of the calculations, but R tells you that you can use a long solenoid formula. You can use this formula. Why? Because R is small compared to the length of the solenoid. So you can use this formula. Okay. That is the assumption, right? Our initial assumption was that the length is much greater compared to the radius of the solenoid. So that was the assumption. So with that assumption, we derived this formula. So this formula can be applied only in cases where your length is much greater than the radius. And that is what they've done here. They gave you this R, they gave you this length, so that you can take a judgment call. Using these two numbers, you can decide whether you can use this formula or not. Suppose if this was say 30 centimeters or something, and clearly you can't use this because it's not a long solenoid. You see, the radius will be much bigger, 30 and then 50, it will be like this. Okay, so you can't use it. Okay. So since the radius is small, it's negligible compared to the length, then you can use a long solenoid formula, and using the formula you find out this value. Hope this is clear to you.